I wanted to illustrate how we can use light clocks to derive the metric equation for special relativity. So if you remember from lecture, this is a light clock and it ticks every time light hits that bottom mirror. So let's imagine that it just ticked and light goes up, hits the top mirror, goes back down, then the clock ticks again. Well, let's consider the reference frame that we just saw. So namely, we're in the rest frame of the clock. In that case, we know that the total path length that the light had to travel was going up and coming back down, so it traveled 2L. Its displacement, of course, was 0. It ended up where it started, but the path length that the light took is certainly 2L, twice the height of the clock. Well, in SR units, that's nice because we can immediately conclude, actually, that that's also the time interval. More specifically, because we have one clock that was present for both events in an inertial frame, it was just sitting there, then we also know that that's the space-time interval, the coordinate time interval, and the proper time interval. They're all equal to 2L in SR units. So let's write that down. Delta S prime equals 2L. That'll come in handy later. You'll notice that I described everything that happens in the clock frame as being primed. So it's the other frame using the notation of your book. What you can imagine we'll do next is sit in a lab frame and have the clock go by us with some relative velocity. That means the clock will be the other frame, our lab will be the home frame. So let's do that experiment now. So now we're sitting in the lab, and we have the same light clock, and we'll start it going. So it's moving with a velocity to the right. The light goes up, bounces off the top mirror, and comes back down. Now I've traced out the path of the light using those dotted lines, and you can clearly see that this path length is going to be longer than 2L, because now it went along the hypotenuse of a triangle going up and coming back down, instead of just going straight up and down. We can figure out what the total path length is, though, so let's get the clock out of the way. We know that that height is L. I'm going to label one of those lengths as being R. So the total path length for the light to go up and come back down has to just be 2R, adding those two paths together. We can form a right triangle over there on the left, and we know actually if we refer to the displacement of the clock as being delta D in our home frame, then the base of that triangle that I just shaded in must be delta D over 2. So we can use this to figure out exactly what the value of the path length, what the value of 2R is in this reference frame. So the path length itself has to be 2R. It goes along each of those hypotenuses. Okay, 2R is equal to 2 times the square root of delta D over 2 quantity squared plus L squared. Where did I get this? Well, that's just the Pythagorean theorem on that triangle that I just shaded in, right? That's the value of R. Okay? So in SR units, we know that the coordinate time interval now has to be 2R. So why is it the coordinate time interval, delta T? Well, you can imagine we had to set up two clocks. We had one when the light first left the base of the clock. We had another over on the right when the light came back and hit the base again. So you can imagine we have a lab filled with all of these clocks so that we can take time measurements very accurately. The coordinate time interval that we would measure would be 2R in SR units because that's the path length of light, and the speed of light in SR units is 1. So delta T is 2R. Well, we have that expression for 2R, 2 times the square root of all this stuff. Now we're just going to divide both sides by 2. And now let's square both sides. So we have delta T over 2 quantity squared equals delta D over 2 squared plus L squared. Now we can use that fact we had before that delta S prime equals 2L. So remember the space-time interval in the clock frame was 2L, but the nice thing is the space-time interval is the same in all frames. So we know that delta S actually has to equal delta S prime. There's only one space-time interval for a set of events, and we already established that delta S prime is 2L. Well, that's nice. That allows us to rewrite L equals delta S over 2. So now let's plug that in for our expression that involves L squared. So now we substitute in, we get that delta T over 2 squared equals delta D over 2 squared plus delta S over 2 squared. Let's get rid of those factors of 2. We cancel all of those out. We'll write it in the more standard form, which is that delta S squared equals delta T squared minus delta D squared. This is the metric equation, and remember it came from considering a light clock in two different frames, a lab frame where it has a relative velocity, and the clock's frame where of course it does not, and then using the fact that the space-time interval between events, namely the light hitting the bottom mirror, had to be the same in both of those frames. That's all you need to derive the metric equation.